Hello, everybody. Good afternoon or good morning or good night, wherever you may be joining us from. I hope you're doing well. I'm Anna Hunsinger, and I am the Vice President of Community Engagement at Internet2, and welcome to today's workshop. Before we begin, just a few announcements. We are recording this event, and it will be available to all of you and to the community after the event. Also, we will be taking questions throughout the session, but the way that we're going to do this is through the Q&A button at the bottom of your screen. And though we're going to do our best to monitor the chat window, but please also feel free to post your questions and comments there. With that in mind, we have some great presentations coming up from the E-CAS participants. And what we're going to do is have them present, and then we're going to have a panel session at the end where we're going to discuss the experience of the teams in using the cloud and have more dialogue about some of the things that they learn along the way. So again, if you have any questions, please use the Q&A at the bottom of your screen, and if not answered during the presentation, we will make sure to get to them at the end of each session. So let's get started, and I'm going to hand it off to the CEO and President of Internet2, and also the PI on this important project. So Howard Pfeffer, here you go.
Thanks, Anna, and welcome everyone, and thanks again for all of those who have participated in E-CAS, and I think we'll have a great presentation, great workshop today, some really exciting presentations. I thought I would just quickly start off with a little bit of how E-CAS came to be, the genesis of E-CAS, and what were the major aims of the program. So, I think it's fair to say that, commercial cloud has really been a bit of a revolution led a revolution in sort of web scale, elastic compute, heterogeneous computing, and increasingly in machine learning and artificial intelligence. And in that context, the aims of E-CAS were to, number one, illustrate the viability of these services as an option for leading edge research across a broad scope of scientific disciplines. Also to accelerate scientific discovery through the integration and optimization of these commercial cloud services. We also wanted to identify gaps between the commercial cloud provider capabilities and the potential for enhancing academic research. And lastly, we wanted to provide some initial steps in documenting these emerging tools and leading development practices and share them with the research and education community. Now, achieving these aims required building some partnerships with the commercial cloud computing providers. And given Internet2's long track record of engaging with the commercial cloud providers on behalf of the research and education community, which includes everything from providing over a terabit per second of peering capacity across Amazon Web Services, Google Cloud Platform, and Microsoft Azure, being part of helping to achieve data egress waivers, for instance, for institutions that are accessing the cloud providers over R&E networks, and with our Cloud Connect service, providing dedicated cloud connections to now over 100 institutions. And beyond that, also offering cloud services that are tailored for the research education community via member evaluated or community evaluated services with common contracting and terms and pricing. Given that context of Internet2 and its relationship with the cloud providers, NSF approached us about a cooperative agreement to lead the E-CAS program. And so, given the expansive set of cloud capabilities, both within and across providers, we structured the E-CAS program as a competitive process so that we could accommodate the broadest possible set of approaches across multiple scientific disciplines. So I think you'll see today that we achieved, I think, the program aims and demonstrated both the opportunities and challenges of applying commercial cloud to leading edge research workflows. So with that, I will hand it off to Jamie Sunderland, who will sort of give a little more background on the program itself, program structure, and we'll move on to our presentations. Jamie?
Thank you, Howard. I joined Internet 2 about 3 years ago, just before the E-CAS project was announced. When I joined, I think Howard and Anna and others had already been in discussions around how the project should be formed, and I joined just in time to help shape what the final version of the project looked like, and of course then won the role of doing most of the project management throughout the program. So let me just share some slides, and we'll get a bit more into the detail of what the program actually entails and what it looked like. So the main goals of the E-CAS project were to work in these two primary classes of study. One being acceleration of science. We were looking at how the cloud could be used to make scientific workflows run faster, mostly through being able to actually run simulations faster or run larger workflows, an ability to process real-time or near real-time streaming data. We also had another category based on innovation. We were very interested in how researchers would be able to take advantage of the facilities that the cloud providers had, particularly in terms of heterogeneous hardware, things such as graphics processing units, GPUs, FPGAs, TPUs, and other AI-like aids to the workflow. We structured the program, as Howard mentioned, into two phases. Initially, the cloud providers were keen to see us do phase one very quickly. The cloud providers were looking for a way that they expressed to us the concern that some researchers had gotten a little addicted to cloud credits, and they wanted to be able to find a way that, while they wanted to provide support to the researchers, they also wanted to at some stage see people actually pay for some cloud usage. So they would have liked to have seen the phase one run fairly quickly. But talking to a few researchers directly, we decided that a year for phase one would be kind of the minimum time for people to actually be able to develop a workflow and turn it into something that they could do using the cloud services. But we also talked to NSF and discussed the fact that what we really wanted to see was the ability to have a serious level of funding available for those who were selected as the best teams, so that they could actually do science really at a large scale. The teams that you can see on the screen are the teams that were selected for phase one of E-CAS. We actually received about, I think it was 27 applications, proposals for E-CAS. We used an external peer review process to shortlist down and then eventually select these 6 teams. And I'll go through a little bit of what those teams actually proposed in just a minute. Our timeline looks like this. We announced the E-CAS program in Supercompute at the end of 2018. We put out a call for proposals, I think it was the 10th of December 2018, with proposals due at the end of January. I went through the review process, had the sub-awards out in March 2019, and then phase one ran from April 2019 to 2020. During that time, each of the 6 teams were able to develop their workflows in the cloud. We held monthly internal meetings and quarterly meetings with the steering committee to review process. Then at the end of April 2020, each of the 6 teams participated in a workshop, a little bit like this one, where they presented the work that they had done over the year. They also provided written reports of the phase 1 work and proposals for what they would do in phase 2. We then went through another process of peer review to review the work that they had done and select the 2 that had shown the best in terms of acceleration of science and innovation. So following that, a small period getting the sub-award contracts done, and then from August 2020 through to August 2021, the 2 teams that were selected have had a year. And during that time, they've had access to up to $500,000 per team for cloud spend and some funding to cover the costs of one postgrad student or staff member. There's also indirect charges available on that cloud spend, so the institution itself could actually claim up to about $880,000 per team. There were a couple of delays, and we'll talk about that later in some of in getting started for phase 2 for a couple of the teams. So we recently went back to NSF and we've asked for a no-cost extension through to the end of this year, just to allow the teams to complete some of the work that they're mostly through. And both of these teams will be presenting today, and I think that's really going to be the highlight of the day, rather than what I'm presenting. I think it's most important to see what's actually being done with the cloud. Importantly, the phase 1 video presentations and reports are available through the E-CAS part of the Internet 2 website. They're also available on YouTube. It's well worth having a look at those because all 6 of these projects were quite good. So I'll just run through briefly what the projects were. I'll probably be very brief on the last 2 because they're the 2 teams that were selected and went through to phase 2. So the first team was from SDSC, the San Diego Supercomputing Center, and they built a system where they could burst Cypress, which is a science gateway used to create phylogenetic trees. It's a very heavily used science gateway with around 20,000 users that they're using, generally the Comet system based at SDSC, submitting over 2,400 jobs a month. They created a system whereby they could essentially transparently burst those jobs out to AWS just by putting a certain tag against the job queue. They used the Internet 2 Cloud Connect to connect to the AWS region in Virginia. The reason they've connected across country from San Diego to Virginia was because Virginia had the biggest density of what was then brand new NVIDIA V100 GPUs. And they wanted to, they found that the V100 GPUs would give them up to, I think it was 2.8 times the acceleration, 2.8 times the processing speed that they were getting on Comet. And also, although they did have a couple of V100 GPUs available through the Exceed program, they were very limited in resources. So it enabled the SDSC team to overcome allocation limitations on Exceed, and they were able to use those newer GPU technologies. There was the second team was from University of Wisconsin-Madison. They were processing data for the IceCube Neutrino Observatory, astronomical neutrinos. This team actually struggled a little initially because of, at the time, at the start of phase one, their university was renegotiating their cloud contracts, and so it did take them some time to actually get access to the cloud credits. However, they also received funding through an EAGA grant, which was demonstrated at SC19, where they actually built a system using the Open Science Grid, and they managed to pull together over 50,000, I think it was 51,000 odd GPUs from all three providers across 24 regions into a big pool to process data. And that was the biggest clustering of GPUs that had happened up to that date. They've since repeated that several times and have looked at more efficient ways of actually doing the processing. The team from the George Washington University, they built a system for Galaxy. Galaxy is a widely used bioinformatics platform, and they built a system called Biocompute Objects, which was essentially a way of packaging up biocompute workflows so that any number of algorithmic steps and variables could be captured within those workflows and attached to the data so that they could actually make those experiments repeatable. This was quite valuable to groups such as the FDA, and they actually, this participation in E-CAS actually led to them being able to get a further grant from the FDA to develop their methodology as a way of submitting applications for drug patents, etc., to the FDA. They built a public instance of Galaxy on Amazon Web Services and made it available to the public. Unfortunately, they weren't selected for phase two, which I'll discuss later. Led to a little bit of a problem with sustainability and funding. The group from Purdue University, I thought this was quite innovative. What they were doing was looking at how urbanization and different city layouts and urban planning affected climate and local area climate. And what they did is they combined techniques from computer vision, procedural modeling, and machine learning to take images of buildings, and from those buildings create 3D models that also identified things like how many windows and doors and what sizes they were and what materials they were made of, etc., to create what they called urban canopy parameters. And those urban canopy parameters could actually be used then to model different outcomes of different urban planning patterns and how that would affect climate and weather patterns. Interestingly, they also used WRF, which is the climate modeling program used by a number of climate scientists, which is generally run on a HPC system. They attempted to run that as well on Google Cloud, but found that they had some issues there. But I'll talk about those later as well. And finally, just a second. Finally, these two you will hear, the next two projects you'll hear much more detail from the actual PIs and the teams themselves, and they will explain it much better than I can. But the first team being from SUNY Downstate Medical Center, they've been using extremely large scale and detailed modeling of the brain cortical circuits to attempt to decipher the codes of how the brain transmits and stores information. During phase one of the project, they demonstrated larger scale of up to 100,000 CPUs and long compute runs using more than 1.8 million core hours over the period of about a week or two. Since then, as you'll hear in phase 2, they've taken that further, building parallel cortical models and much longer compute runs, etc. But I'll allow them to talk about that. And then finally, the team, which will be up next in about 8 minutes' time to talk about their work from MIT. They were looking primarily at the heterogeneous computing for the Large Hadron Collider. This is a fire hose problem, you know, trying to find a grain of sand in a fire hose. And the focus initially was around creating machine learning as a service to take their algorithms and design a new version or a better version of the high-level trigger at the LHC, and to be able to offload algorithmic machine learning algorithms to the GPUs, and then design how many or the ratio of CPUs to GPUs which were needed for the workflow. Since then, they've extended that concept and have achieved some great results with reprocessing LIGO data, for example, and several other areas of machine learning in high energy physics. So you will hear about that in about 5 minutes' time. So there's a little wrap up of what the foundations of the E-CAS project are. We're approaching the end, and hopefully, well, not only hopefully, I know you'll get to see some very good outcomes, particularly of those 2 projects that progress through to phase 2, and that's coming up in about 5 minutes. But if there's any questions, I'm happy to take questions now. Otherwise, we'll pause for 5 minutes or so, and then we can start with the high energy physics team on the half hour. So thank you. I'm not seeing any questions come through at the moment. If anyone has any questions about the program, happy to answer. Failing that, we can hold it here for a second. It's also a good thing because we can pause the recording so that we can segment it later for publication. So if everyone wants to take a 5-minute break, we'll be back on the half hour, and I'll introduce Dr. Philip Harris from MIT, and he can introduce his team and continue in that section. Thanks. Okay, for those of you who've just joined, thank you for joining us here at the E-CAS Phase 2 workshop. I'm pleased to introduce Dr. Philip Harris from MIT, and he can introduce his team, which are from a range of institutions, and his team was selected based on their level of innovation in phase 1 and awarded to continue through to phase 2 of the E-CAS project. Please welcome Dr. Harris, and please take it away, Phil. And
great. All right, so thank you. Yeah, thanks to Internet 2 for these awards. We've done really a lot of stuff, and this is a snapshot of our team. So there's really a lot of people involved. This is a relatively big group of people. And I just kind of wanted to mention, right, a little bit about who we are. So this started basically as a project of like LHC physicists. So myself, some people at Fermilab and CERN. And we've been trying to grow this over the past few years to kind of build it out. And the idea is that we want to take machine learning algorithms and we want to use specialized processors to make machine learning algorithms run really fast, right? And we need this for the LHC. So the kind of data rates that we're talking about are just enormous. So if you were to take all the data from the LHC, we're talking about something like half a petabyte per second, which is larger than any other data source in the world. And the idea there is we want to process information as fast as we possibly can so that we can see if there's hidden physics in the data. Since then, though, we've expanded this project to many other fields. We find that there's a lot of interest to run AI algorithms fast. And there's a specialized skill set that you need to really kind of take advantage of new processor technology if you want to really run this fast. So what we did in this part, the E-CAS part of this project, is that we focused on three main big science drivers. So we focused on LHC physics. We focused on also protodune. So protodune is a large neutrino detector that's it's a precursor to the Dune neutrino detector that's going to be built to Fermilab. And then we also looked at gravitational wave detection in the interest of trying to understand how this work interacts with astronomy in general, right? And astrophysical signatures. So that's going to be what I'll show you this, or what our team's going to show you in the next hour and a half. And we'll talk about various different aspects. Last year we started with the LHC, right? So we, as LHC physicists, this is where we started. And our idea here was to see how we could integrate kind of GPUs and FPGAs into the computing workflow of the LHC. And in the first year we did kind of a proof of concept that we could do this. And the way we did this is we used the fact that in the cloud, we have access to resources that are just not available at our normal computing sites, right? Access to GPUs, access to FPGAs at scale. We also looked in the first year at TPUs. And so this new processor technology in the cloud allowed us to kind of run tests and studies to kind of demonstrate how we could integrate these new processors into the system, and also allowed us to kind of understand how fast we could run AI. So we did this in the context of the LHC, and actually at the end of the project, we added the protodune detector. We found an algorithm that we could run with neutrinos, and that kind of carried over to the second year. So our conclusions from last year was that we demonstrated for the first time machine learning as a service can be deployed at the LHC and other high bandwidth experiments. So in that case, we meant the kind of Dune or the proto-Dune. And we saw that actually if you manage things appropriately, you could actually make this very cost effective, right? In particular, we see that GPUs and FPGAs can run algorithms as many as 1,000 times faster than on a CPU. And so you have to come up with a new computing model, right? And so over the first year, we started to build an inference as a service computing model. And in the second year, we've kind of expanded this to kind of run this in realistic scenarios. So what we developed, at least in the first year, we had a first version of a system like this, where we actually take our kind of existing CPU infrastructure on the left, and then we take an accelerator. So, and this could be an AI accelerator. So some special processor that can run a specific algorithm very fast. So in AWS, we use the F1 instances. So these are FPGAs. In Google Cloud, we actually tried this with both GPUs and TPUs. In year one, we concluded that TPUs are really not the right application for us. They're much more useful for training, not for kind of processing large amounts of data. We can talk about this at some point. And so in the second year, we actually focused on GPUs and FPGAs, and we focused on kind of bringing the system from just a first working system that showed that we could get speedups to something that we could legitimately install in the detector and start running, now. And so that's been our goal for year two. This builds on all sorts of tools, right? So tools from industry for GPUs. We use a so-called trained inference server, right? For FPGAs, we actually wrote our a whole set of infrastructure. We'll have a talk on this. And then, kind of the important thing that we learned from year one that we're now expanding on is the computing model, right? We realize, computing centers at the LHC and, at LIGO and at ProtoDune, they tend to be very CPU heavy, right? So there are many CPUs. CPUs are great because you can run whatever you want. But, we found that even just adding one GPU, if it can run an algorithm, hundreds of times faster than a CPU, you can speed up the whole system, right? Just by adding one CPU. And so building a model where we can integrate the CPU and have it talk to many, or have a GPU talk to many CPUs over network was part of the challenge. And actually building a model now where we scale out to not just one GPU, but, tens or even hundreds of GPUs and, tens of thousands of CPUs is what we've been exploring in the second year. And this is all thanks to the fact that, certain algorithms, when you run them on these specialized processors, can just run really fast, right? As much as, 50 or 100 or even more. Okay, so how do we build on this? Well, the one thing I will say is that we're in some sense standing on the shoulders of giants. So our work has been closely connected with the work of a so-called HepCloud. So this is a project that was developed a few years ago, and it allows us to kind of do large scale out tests in the cloud. So this is a grid submission tool. It's based on HT Condor, and it allows us to submit tens of thousands of jobs to the cloud. So here's actually a CMS. So this is production of LHC data. And you can see that we can double kind of the compute of LHC data with HepCloud. So we had this tool already in hand when we started this project. And this allows us to kind of tinker and build, specific systems. And then when we're ready, we just push a button and we scale out the whole system to LHC style scale. We're talking about tens of thousands of cores. So what resulted from our first year? So in fact, our first year inspired a lot of people to start thinking about this work at future directions. So at the LHC, there's now a lot of discussion about how we can incorporate GPU and other hardware accelerators into the compute model. What we've also seen since we presented our work after the first year is that a number of LHC computing centers have started to purchase GPUs. So at MIT, actually, we purchased several GPUs, as well as computer centers across the globe, right? They all now have a handful of GPUs. This is not the same amount of GPUs that we have access to in the cloud. It's kind of a first step in that direction. But it was motivated by the success of what we saw that we could do in the cloud, right? Using it as a lab. And, on a longer time scale, the stuff that we developed through this project, we're working to kind of bring this to DOE and NSF high performance computing centers. And this includes Exceed, NERSC at Berkeley. And so we're working actually to take what we learned in this project and bring this to the HPCs. What I will say is that, when we started this, we couldn't do anything with these, right? Out of the kind of the setups that we have, we're not really designed for, or the HPCs are not really designed for the setups that we have, where you have many CPUs and a handful of GPUs. But we're starting to kind of experiment and push on these HPC centers, and we're starting to get some ability to do work there, but it's still a long journey. The systems really were not envisioned for this kind of processing. So having the cloud and being able to have the kind of full configurability has really made a big difference in terms of how we go forward for big scale scientific computing. Here's some kind of fun articles you can read about our work. To go into a little bit more specifics about the second year. We started kind of in the first year to build tools. So we built this tool called Sonic. as well that built on kind of NVIDIA infrastructure. It also, we were able to integrate this with our FPGA compiler, HLS4ML. And this tools allowed us to run GPU and FPGA as a service, which we ran in the cloud. In the second year, we wanted to take Sonic and actually ask all the questions, what are all the details that we need to bring this to a fully realistic processor, right? or fully realistic system, right? Something that we could run in LHC production or, Proto-Doom production, or even in LIGO in the real-time system. And so we actually spent a lot of time in the second year kind of developing the Sonic infrastructure. And now it's much more mature, and it's the kind of thing that we can actually run full LHC workflows with. So that was a big effort, and we'll hear more about that. In terms of the other work, we worked on trying to expand the functionality of our tools. So FPGAs actually, we very dramatically expanded the kind of scale and scope of models that we can use. So you'll hear more about that. And for GPUs, we've now kind of gone not just from kind of a simple inference as a service kind, but we're now dealing with not just AI algorithms, but rule-based algorithms. We're dealing with kind of a broad range of scenarios. We're not just running one or two algorithms, we're running much more complex setups that are fully realistic in our production. So here's kind of the sub-projects that we split into for year two. So the blue here are continuing efforts from year one, and the red are new efforts. So in particular, we've been working on kind of developing a new or integrating a new AI architecture known as graph neural networks. So that's an effort we've been continuing to work on in the first and second year. But we also added other types of networks, such as fast point cloud neural networks. We developed a multi-FPGA deep network infrastructure. And then we've also developed, we've also then kind of worked on deploying these in large scale systems. And so now we're running a CMS high-level trigger emulation with a large set of GPUs. And you'll hear about some reconstruction of neutrino events with Proto-Doom, as well as LHC, offline detector reconstruction. We added a new domain, so reconstruction of gravitational waves, and so you'll hear a lot about that later on. As well as we did some more exploratory work, such as model-independent searches, and then kind of designing other new AI algorithms. And actually, and to cap it off, we also had a number of different educational efforts that we'll talk a little bit about. So the focus of the talks after me are going to be on the three main thrusts, right? So LHC physics, neutrino physics, gravitational waves. In addition to these thrusts, there's actually a lot of other papers that have come out of this cloud use. What we found is that a lot of in addition to kind of these large scale deployments that we're running, we allocated some money to just do R&D, right? Algorithm design. And we found that actually in the cloud, we could do R&D much faster because we had uninterrupted use of GPUs, right? This is not something, for example, at MIT, we have maybe 2 or 3 GPUs that we could use. We don't have access to like a large number of GPUs where we could do large scale deep neural network training. And this allowed us to kind of develop algorithms at a much faster pace than we could, in our current setup. And so I'm just going to flash through some of the stuff that happened, or some of the algorithms that we've developed in the past year. And we're not going to talk too much about this beyond it, but suffice it to say that this is something that we got kind of for free from the cloud. So here's on the top, here's an algorithm where we actually made a simulation that generates clouds of particles. So we can actually this is for LHC particle simulation. This is the left is the network architecture. And suffice it to say, you can go through these papers, but we have a first algorithm that actually can do very realistic particle level simulation in the cloud. The bottom is actually the opposite. So instead of simulating particles, we reconstruct particles from detector inputs. And this is an algorithm that can take about order 5,000 detector inputs and reconstruct 1,000 particles in one inference of this AI algorithm. So this is an AI algorithm that does that. So this allows us to run this kind of reconstruction really, really fast, right? So when you put this on a GPU, it's much faster than our previous rule-based algorithms. The top here is a new algorithm we're looking at. It's not complete, but here's a promising diagram of how it works. And the idea is to actually take energy deposits at an LHC collisions and cluster them into particles. The kind of interesting thing is that unlike our current algorithms that can do one cluster at a time, this one can do 1,000 clusters at a time, right? On a single kind of AI inference. So you can have very heavily parallelized your computing and run much faster. And the bottom here is a very exploratory thing that uses some ideas from unsupervised learning to kind of make a system that can look for physics events that are just completely unpredicted. And here's actually a test. We entered a competition last year, and we had very promising results where we actually discovered a new physics signature in a toy set of data where this signal was hidden. And so this was developed as well in the cloud. Here's just a flash of all the papers, and this is just year 2. So suffice it to say that having these cloud, the functionality in the cloud really expanded the scope of our work. So all of these papers came just in the past year, and they're all use the cloud in some way. So this is a real, help from the E-CAS project. It expanded the scope of science that we could do by a lot. In addition, right, we have various educational efforts. We had actually 6 tutorials over the past year. And in fact, Dylan in his talk will talk about, actually, we got sick of having tutorials. So we just decided to host an online tutorial in the cloud. And I'll let Dylan talk a little bit more about this. We also had 2 conferences focused on this. So we had a conference here focused on big data experiments, so the LHC as well as astrophysics experiments. And then we also hosted our annual fast machine learning workshop. This first workshop had something like 150 attendance. The second one had on the order of 250, 300 attendance. So we're getting a lot of press for this work. As well, this has been presented at various different venues. I think this list is a little incomplete. Our ultimate vision in the end is we want to kind of combine science, our AI algorithms, right, and computing hardware, and understand how these 3 tools coexist and how you can really take advantage of all of them. And we've been doing this in the context of big experiments. So we focused on the LHC, right? And we added now the Dune experiment, but now we're looking at other experiments such as LIGO. And in the future, we're thinking about work with IceCube, ZTF, and so on. Okay, thank you.
Would you like to take a question or 2 now, or would you prefer to move on and introduce the others?
Either way, maybe we should move on, actually.
Yeah, move on. I'll hold 1 or 2 questions and see how we are at the end.
Okay, sounds good. All right, so next on our list is Kevin. Can you share?
Right, all good?
Yeah, looks good.
Okay, so I'm going to give an overview of services for optimized network inference on coprocessors, or SONiC, which is our approach to using coprocessors as a service to do inference for the LHC. So first, putting things in some context, this is the schedule for the Large Hadron Collider, showing the early runs that have already happened. We're currently during the second long shutdown here in 2021, and soon we will start the third one of the LHC. Now, the instantaneous luminosity, which is related to the collision rate, the LHC increased throughout runs 1 and 2, as you can see in these red lines here at the bottom. And now in run 3, we're going to spend the whole run at a full factor of 2 above the actual design luminosity for the machine. And so this will deliver the largest data set so far at the highest collision rates. And in particular, this also means that there will be more simultaneous collisions per bunch crossing, also called pileup. And this makes all of our events more complex and take more time to reconstruct. And further in the future, we have the high luminosity LHC upgrade, which is run 4 or 5 and beyond. This will further increase the collision rate as indicated. So we'll get about 10 times more data and multiple times more pileup than we currently have. And in addition for this upgrade, our detectors will be upgraded accordingly, and the number of channels will increase by more than a factor of 10 for a number of our most important detectors. So, as you might have guessed already, this high luminosity upgrade poses a number of challenges. On the left here, I'm showing a visualization of how much data we'll collect, and you can see in run 2, we are collecting still a large amount of data, but comparable to other experiments and other industry companies at that time. You can see projected out into the HLHC era, we're going to have an exabyte level amount of physics data, and other big experiments are going to have similar amounts getting up into the multiple tens to hundreds of petabytes. In addition to these huge data volumes, we won't just have more events, but it'll be more complex. As I mentioned, we have more pileup, more detector channels, so we're going to have a lot more information that we have to process. You'd expect then that we need a corresponding increase in CPU, but CPU clock speeds have been stagnant since about 2005, while Moore's law continues in terms of increasing the transistor density. Denard scaling has no longer been able to continue, so the clock speeds have basically stayed the same. And you can see the impact of this on this projection up in the left, where we show the amount of processing we actually need to do in blue, and then the gray band shows what we can actually expect from CPU resources if things continue the way they are. So clearly there's a large shortfall that needs to be addressed, and we need new solutions to process this data effectively. And this brings us to inference on coprocessors. So new coprocessors like GPUs, FPGAs, and ASICs provide efficiency at the expense of flexibility. So you can't do as many kinds of operations, but those operations that you can do much faster. This poses a little bit of a problem for us in principle because our classical HEP reconstruction algorithms are extremely complicated, and they're definitely difficult to re-implement and maintain in coprocessor-specific languages like CUDA. Though this is sometimes necessary because you really need that exact algorithm. And so to make this a little bit easier, we're investigating portability libraries that will allow the same algorithms to be compiled to different machines. But overall, our view is that it's more effective to recast these HEP algorithms as ML algorithms. Because ML algorithms use a restricted set of operations like matrix multiplications, et cetera, but really implement pretty general function approximations for various tasks. In addition, we can also benefit from massive industry investments in ML, so we're not just out there on our own, but we're taking advantage of everything else that's going on in the world. And in particular, ML algorithm inference is naturally suited to be accelerated by coprocessors. And then we come to how we deploy these coprocessors. So the naive way to do this would be to do direct connection, where each CPU node is connected to some coprocessor. This means, of course, you have to purchase one coprocessor for each CPU node, which can be quite expensive. So instead, we propose to use coprocessors as a service. And this simplified diagram here shows how it would work. Multiple CPUs can send inference requests to multiple servers. And one server could be using GPUs for certain models, another server could be using FPGA for other models. These CPUs don't really need to care, they just need to get the result of their request. The nice things about this as a service approach is that it ensures optimal utilization of GPUs and FPGAs. In the direct connect case, if you don't have enough work to do on the GPU, it will just sit there idle. Whereas in the as a service approach, we can make sure that it gets enough work to do, so it's always being used. This also makes it more cost effective, and it makes it more flexible because you can rearrange how these servers are deployed on the fly. So now this brings us to the sonic approach, which is the title of this talk. This approach is how we use coprocessors and do inference as a service in the experiment software framework. And in particular for the CMS experiment at the LHC, this is enabled by a feature called external work, where we can do asynchronous non-blocking calls so that the other work on the CPU continues while the coprocessor is doing its work separately. And this is the most efficient way to do this sort of thing, and it means that you're really not subject to latency up to the point, at least, that your CPU still has other work to do. One big benefit of Sonic is that it lets us integrate a lot of industry tools, as I was mentioning before. We use the Google Remote Procedure Call library for client-server communication. This is very efficient. We found it to be a lot faster than other ways of doing that, like HTTP. We can use off-the-shelf inference servers, or we can build our own similarly, and I'll talk about that in the next slide. And we can use technologies like Kubernetes for dynamic scaling of resources and interaction with the cloud, which of course has been facilitated by the E-CAS project for us. But there are more benefits to Sonic than just these things above here. We also get simplicity because the modules in our experiment software framework only implement the input-output conversions for the data, and all the actual inference processing is done on the server. So we've abstracted that part away. We don't have to re-implement it. We also get containerizations. Modern machine learning frameworks are very complicated, and it's hard to integrate all the code together with our experiment software that's also very complicated. In the as a service approach, these frameworks are hosted separately, and so you don't have to worry about that compatibility. And finally, we also get portability. As indicated, because ML algorithms are naturally suited to inference on coprocessors, it's easy to move them around between different coprocessors. And this means you can swap between CPUs, GPUs, FPGAs, and so forth without changing your code at all. You just run the exact same thing that you would have run before. So a few more details on our inference servers. The main one that we've been using for GPUs is NVIDIA Triton. This server has a ton of features, and it's open source, which is great for us. It supports all backends, all the ML ones, and even the non-ML backends. You can do custom code running on this server. It supports dynamic batching, so you can combine multiple requests to get better throughputs. You can have multiple GPUs in the server, and it will load balance between them. You can optimize machine learning inference using TensorRT. It does things like using reduced floating point operations, merging layers, and so forth. If you do have a local processor, it's more efficient to use shared memory than gRPC, and that's also supported. We've recently added here I/O compression, so you can trade between CPU and network bandwidth if that becomes necessary. And there's a model analyzer that tells you how to optimize your deployments in the server. Now, with this idea in mind, we actually developed our own FPGA as a service toolkit called FAST. And this is also open source. We use HLS for ML, or the Xilinx ML suite, to deploy models in FPGAs. That's on the server side. And then on the client side, we use the same gRPC calls that Triton does. And this is by design, because that means you can swap between a GPU managed by Triton and an FPGA managed by FAST with the exact same client code. Literally no changes are needed. So a little bit more detail now on what we've been doing with Sonic. We want to be able to predict what kind of performance gains we can get. And for that reason, we've put together a computing performance model. It's inspired, for example, by Amdahl's law, where if you take a serial part of a program and make it parallel, then you can predict the speed up and latency based on what percentage of the program is now parallel and what percentage is still serial. And that's shown for different cases here on this plot on the top right. So instead, we define this GPU to CPU replacement factor called F here, and it's defined for a given algorithm. And it's based on the CPU processing time, X, the overhead from I/O processing in Sonic, which is S, the rescheduling time, L, which depends on both the GPU processing time and the transfer time between the client and the server. So you put all these things together in this fairly simple formula, and you get F, which gives you the maximum number of CPUs that you can replace by one GPU for this algorithm while maintaining optimal throughput. And then if you go too high, so you try to replace too many GPUs with an equivalent GPUs, then the GPUs will saturate. They won't be able to do all the work you're asking to do, and the processing time will increase. But up until that point, you can keep replacing a bunch of CPUs with that one GPU. And here I've actually shown an example from our proto-Dune studies because it's a little bit simpler to evaluate the model since we're only accelerating one algorithm in this workflow. Basically, what you should take away from this plot is that if you look at the dotted lines, they show what our model predicts, and then you look at the lines with markers and they show the data that we actually got from running. You can see that our model does a good job of predicting where the saturation will start, and that lets you know basically how many CPUs you can replace with that one GPU, so you can use it optimally. Now a bit more detail on CMS data processing and how we fit in. So the LHC delivers about 6 million events per second. Physically and financially impossible to store 600 terabytes per second as much as we might want to. So instead, we have to try to select interesting events, and we have to make these choices correctly and quickly. At the level 1 trigger, which is implemented in FPGAs, the latency budget is only about 4 microseconds. The high-level trigger, which is implemented in a custom CPU farm, the latency is about 200 milliseconds, so it's a bit more of a budget, but it's still a pretty tight amount of time to make this kind of decision. So we want to deploy Sonic here as well as offline to facilitate the integration of coprocessors. And what we want to do here is improve these steps by making algorithms both faster and more accurate. ML can give us better answers, not just faster answers. And we can also use non-ML GPU implementations with CUDA if they're available. In addition to improving these high-level trigger and offline steps, we can also enable new data streams like scouting, which CMS has done before, but can be improved a lot using this ML approach. Here, essentially, you only keep a subset of the data as it's considered at the high-level trigger in this 200 millisecond latency, and then you just do analysis on that data exactly offline. So it's a much smaller event format, and these are basically pieces of information that would have otherwise been discarded, but that you can still get some useful physics out of. So if we can streamline this whole approach, we can get much better information in the scouting stage. Now looking toward the future, at the HLLHC, we've been doing projections of what our processing will look like at the HLT for phase 2 in the HLLHC. And what you can see here is that the reconstruction for our new detectors, the high granularity calorimeter, where we have to do clustering, and the pixel and tracker system, where we have to do charge particle tracking, essentially dominate this time. They're about a similar amount of time is spent clustering and tracking, and they're overall, about 80% of this total HLT for certain events. And the reason for this you can see in the bottom. So here's a simulation of the HGCal with 200 pileups. So there's 200 collisions happening in one event, and these are all the energy deposits you get from them. And these are all colored by what particle they came from. So your goal then, if you just had all the individual hits in the calorimeter, would be to put all these particles back together as clusters. Naively, this means you have to compare every hit to every other hit, and this would take about n squared time if you have n hits. With classical improvements to your algorithms, you can get to about n log n at best, but we still want to do this even faster. And it turns out ML can actually help us with this. And it can do this by using graph neural networks. So we've been developing these graph neural networks in order to satisfy these problems. And Phil told you about a few of them before. I'm going to tell you about a few more. Basically, these graph neural networks constitute an advancement in machine learning. They let us perform low-level, time-consuming reconstruction tasks, taking a step beyond the standard classification and regression that they're usually used for. And we find that so far they have competitive accuracy and significantly better scaling. And the scaling here, you can see, this is from the Exatrax project, where you get definitively subquadratic scaling with the number of hits for LHC tracking problems. And you also get high efficiency, as shown as this plot on the left. We're also working on applying the same kind of algorithms to the clustering problem for the HGCal. And here's an example of one event where we compare the true clusters to the ones that are algorithm prediction. You can see it's almost indistinguishable. So we're really able to essentially put all the hits back together exactly the way they're supposed to be and do it pretty quickly. So this means that if all these efforts converge, this is a major value add for Sonic in the HLHC runs because we can accelerate all of these algorithms very efficiently. And this also gives us, in this E-CAS project, synergy with a lot of other groups like Exatrax, LDRG group funded by Fermilab, and people working at CERN as well, who are developing these kinds of algorithms. And we're not just developing them for physics, we're also optimizing things like k-nearest neighbors and other custom kernels to run faster on coprocessors, and then specifically to be able to deploy graph neural networks and FPGAs, which had not been done before we started doing it in this context. We also have a few more applications of graphs. So if you take the idea from before and put it into what's called a dynamic reduction network, it actually learns the best way to connect the inputs and then uses that to do regression tasks, for example. Here you can see that we actually can improve the resolution of electron energy by 10% versus state of the art. And this might not seem like a lot if you're not familiar with the context, but the state of the art has been around for quite a long time and no one had been able to improve on it until we put this technique into practice. We're now trying to apply this to missing energy, which would also be a huge improvement. And in fact, this may be deployed at the CMS in Run 3. And right now, because of details of the network, it would actually only be deployable via Sonic. So this is another case where Sonic lets us do things that we couldn't otherwise do. We also have a project on semi-supervised learning. Because you know which vertex in all the collisions in the pileup that the charged particles come from, you can train this only on data to distinguish between pileup and the hard collision that you actually want. And so when you do this, you can see there's a significant improvement versus the classical algorithm. The jet momentum resolution, for example, is quite a bit narrower than it would be if you use a classical algorithm in pileup conditions like we'll have in the HLLHC. So time to finish up. The HLXC presents extreme computing challenges, and we think that coprocessors as a service are a viable approach to meeting those challenges. It lets us make a flexible and cost-effective use of GPUs, FPGAs, and more. Sonic provides mature tested client server interfaces for HEP experiment software frameworks. I've been focusing on the CMS case, but we've also implemented the same interface in the software that's used for the Dune experiments. And we are, happy to expand this to other experiment software where it's viable. Our focus is primarily on ML algorithms because they're easily accelerated, portable, and we have synergy with industry. And in particular, we think that graph neural networks have the most promising scaling at HLLHC hit occupancies. Next, you'll hear about the performance of Sonic in realistic production workflows, which was facilitated by cloud infrastructure, which let us test these GPU systems at scale and validate our computing performance models. And this in particular can serve as a template for the usage of HPCs and other leadership machines in the future. Thanks.
Thanks, Kevin. I think we'll continue to hold questions off till the end and see if we fit in time. So I think we're passing over to Patrick now.
Great. Yes, let me go ahead and share. I dropped a Dropbox link in the chat.
I can see that.
Share this, going full screen. Great.
Looks
so hopefully
good.
you can see this. Yeah, so I'm Patrick. I'm going to be talking about LHC computing, sort of picking up from where Kevin left off. So the question basically is, how do you go from an actual proton-proton collision that maybe produces here a Higgs boson and actually know that you had your Higgs boson? So Kevin already covered this. In coming years, our data is going to become more complex and come at a much higher rate, which is a big computing challenge for us. So what we want to do is exploit heterogeneous computing architecture, and in particular, use inference as a service. So this is what Kevin was spending the last 15 minutes on. And just as another really quick reminder, the CMS data flow, generally what happens is we have our proton-proton collisions. The events have to pass a 2-level trigger. And then finally, physicists can actually look at the data that comes out. And for us, we foresee using inference as a service at 2 steps in this process: at the high-level trigger, which is the second part of the trigger, and then in the data analysis stage. So the first part of that 2-level trigger is really hardware-based, so ASIC and FPGA-based algorithms, which are rather coarse. However, the HLT stage, which is ripe for inference as a service, uses more sophisticated algorithms to sort of deduce if there were interesting physics objects, so maybe a higher energy electron in the detector. So the HLT runs on a CPU cluster of over 30,000 cores, and each event right now takes about 400 milliseconds to process. So of course, these coming challenges that Kevin was talking about are going to drive up this per event latency to maybe over a second per event. Now, there is a plan to use heterogeneous computing to help prevent such a dramatic increase, but it requires the purchase of about 800 GPUs. And of course, this is contingent on the fact that we know that HLT algorithms can be accelerated with coprocessors. And hopefully Kevin convinced you that the inference as a service framework will optimize heterogeneous computing and reduce our costs. So do we really need those 800 T4 GPUs to service the HLT? So after events pass the trigger, how do we analyze all that data? And we're talking many petabytes per year in the current environment. There's sort of a 4-layer computing grid is what we call it. So we have tier 0, which stores the data on tape and redistributes that. Then tier 1, which stores a subset of the data. And then tier 1 and tier 2 combine CPU resources to do processing of the data. And what do I mean by processing? So your average physicist day to day doesn't really care about a single hit in the pixel detector or a single hit in the calorimeter. They want to do an analysis that involves electrons or 2 muons or a jet that looks like a Higgs boson or something. So this high level information is what we're trying to extract in our processing of the data. And this follows through a chain of increasing slimness and increasing high levelness. So the raw data is, of course, just detector hits. And then at the mini AOD stage, you have something like a collection of particles that looks as if it's a Higgs boson or a boosted Higgs boson, something like that. And we do these, the mini AOD production stage monthly, and it takes multiple days to run. So this is not something that's cheap. And we do this reprocessing because our algorithms are continually being updated. And in particular, there's an increasing usage of machine learning algorithms at the mini AOD stage, and even starting to trickle upwards into the AOD stage and into the HLT. So since we're starting to use these ML algorithms, we know that we can use heterogeneous computing and therefore inference as a service to reduce our processing times. And really a very big picture idea here is to essentially use the cloud as a tier 2 site. Because if you remember, these tier 2 sites, they often don't have GPUs, which makes it impossible to do heterogeneous computing. The cloud is a really great place with lots of CPUs and lots of GPUs. And I think Phil mentioned in his talk that we have this paradigm called HepCloud, which basically simplifies cloud computing for physicists and allows us to perform large scale-out tests. It's based on Condor. You submit your jobs, virtual machines get spun up automatically, and they run in the cloud as opposed to running on local resources. But the submission code is very, very similar. So our initial studies here, we're taking the calorimeter algorithms, which we knew could be converted into basically a machine learning form. There was really no previous existing infrastructure for inference as a service here, particularly with GPUs. But we knew that if we machine learning-ized our calorimeter algorithms, we can get these significant speedups. So this sort of motivated us to develop this infrastructure. And also along the way, as Kevin was mentioning with the Amdahl's law slide, basically we also developed a way to take our expected speed up and turn that into how many, or like essentially cluster design, how many GPUs can service one CPU. And so there were a few different algorithms that we tested in terms of complexity and number of simultaneous inferences you need to be made. And we see some really great results here. So these ML-based algorithms can replace the current versions of the calorimeter algorithms. And when, for example, you run this facile algorithm, you can get a speed up of 10% for the entire HLT relative to the baseline HLT algorithm, which is a significant speed up, and it basically eliminates the latency due to the HCal, which is part of our calorimeter. So we also saw that we could service basically 300 HLT instances by a single GPU. Basically that scales out to meaning about 10 GPUs for the entire HLT, as opposed to that 800 GPU number that I think I quoted many, many slides ago. And since these plots were made, we've actually done some further optimizations. So beyond making a lot of efforts to really integrate machine learning as inference as a service into CMS in general, and performing physics performance studies, a lot of work was done on throughput optimization. So by making a few changes, such as compressing our data flow, and then making a tensor RT conversion of the model, we can actually get another throughput increase of over 4 times. So bumping us up from 500 events per second to over 2000, which again would increase the number of GPUs, or sorry, the number of CPUs that a single GPU could service based on the Amdahl's law of scaling. And just as a note, stay tuned for Dylan's talk, because he's going to talk about putting Facile on FPGAs. So the HLT calorimeter algorithms were a great initial place for us because we knew we could MLize some algorithms. So with all the work that we've done in the past years, we now have a pretty mature infrastructure that's fully integrated with CMS software through Sonic, which is what Kevin was talking about. So what we've done is made a mini AOD production demonstrator. So that's a part of that offline production flow that I was talking about. And this can be deployed in a variety of contexts. So one is Google Cloud, of course. This is basically what I was sort of suggesting as a future tier 2, essentially. So sort of arbitrary large number of CPUs and plenty of GPUs. Then there's also, we've been doing testing on a current tier 2 site at Purdue. So this tier 2 actually does have a few GPU resources available for testing. And then lastly, we've been testing at basically a high performance computing cluster in Taiwan. So this is basically what a computing cluster might look like in the future, where it actually does have a large number of GPUs available. So the mini AOD demonstrator that we developed sonicized a few of the models that are used in the mini AOD production, but those models actually account, or those algorithms really account for over 10% of the total mini AOD production latency. These are just relatively straightforward to sonicize. And of course, coprocessors, once you use them, actually will, of course, basically knock that number way down. So what we've seen with this demonstrator is that in all contexts, we see speedups when using inference as a service, peaking at around 10% in the throughput, which is a very significant fraction of the 12%, of course. And at the Google Cloud and Purdue, we see that one GPU can service at least 60 CPUs. We haven't actually fully saturated the GPU usage in GCP, so that number can go higher. And we're still optimizing these final numbers. So like for some of the algorithms, for example, you could imagine, or we could expect increases up to like 1,000 CPUs per GPU. But some of the other algorithms, since there are basically 3 of them, don't have the same speedups. And so what we're doing here is optimizing our setup. So with these tests, we're submitting jobs from Purdue Tier 2 that are using a Triton server that's living in the cloud with different model configurations. So you can imagine one server on one GPU that has one algorithm on it, and then a different server on a different GPU using a different algorithm or servicing a different algorithm. So that'd be one potential setup, or you could have 2 GPUs with both of the algorithms on them. We're just testing different configurations essentially to try to optimize our throughputs. And then the very next step after that, of course, is a scale out. So submitting a really large test over a very large data set where we use, say, 10,000 cloud CPUs and Triton servers with maybe 100 GPUs or so. And so now we can look back at the HLT, which is what I was talking about with Facile, and those initial algorithms. So in addition to those calorimeter algorithms, which now we have implemented into CMSSW, the MLized versions, there's also a GPU native tracking procedure called PataTrack, which is our first non-ML algorithm that we've implemented inference as a service for. So we had to create a Triton custom backend for this. But we know that basically if you put the calorimeter algorithms and part of the tracking on GPUs, you can reduce your per event latency by a factor of about 1/3. And there are also concurrent efforts basically to more or less put everything else on coprocessors that are sort of ongoing. So what do we see when we run Patatrack, both standalone and as a service? Well, we actually see pretty similar numbers. So the standalone Patatrack can get you to 500 to 1,000 inferences per second. So 2 milliseconds to 1 millisecond per inference, which of course is a very tiny fraction of the total per event latency. And we see basically very similar numbers for the inference as a service version that we've written. So what does this mean? This means that Patatrack, if we run inference as a service, we can hopefully get that to service 500 to 1,000 HLT nodes. Since the latency is pretty small, that it accounts for like less than 1% of the total per event latency. Multiple CPUs can just send requests for inference to the server and get it back by the time the event is finished running. So the current projection, the one that I mentioned in one of my very first slides about having 800 GPUs for the entire HLT, in that context, the idea is to have one GPU service 32 cores, which is one HLT node. What we think we can do with inference as a service is reduce the GPU purchase requirements by a factor of 10 to 30. So maybe one GPU can service 300 cores or so. So either this is going to save us money, or we can just use those GPUs if we end up buying a whole lot and use them somewhere else, because GPUs are always useful these days. So moving forward, after the demonstration that we made in the first year, there were a few concerns that came up. The main one being, can we actually do inference as a service at full scale? And this is what we're going to be doing this month, is a full HLT mockup. So the last slide hopefully showed that our preliminary results suggest that we can use about 10 times fewer GPUs than the current scheme for heterogeneous computing. So our final tests on the cloud are going to be running this full system with 10 times fewer GPUs and seeing if it works. So this would really be a full-scale test. And this is really the culmination of everything that we've been doing up to here, and basically is the hardest part of the LHC studies that we've been working on. So just to make some quick conclusions here, hopefully we've convinced you that inference as a service is deployable at scale for the LHC, which we both demonstrated in the offline computing flow and in the HLT setting. It's a cost-effective way to solve, or at least alleviate, some of the computing challenges that we're facing within 5 years or so. We know that we want heterogeneous computing. That's kind of a given. But inference as a service can really either save us money, quite a bit of money, or get us more bang per buck. And lastly, the integration of inference as a service into the CMS computing paradigm really is part of the decision-making going forward. So this is not some immature idea now. This is really something that's motivating what we do at CMS. So that's the end of my talk. Thank you very much.
Excellent. Thank you, Patrick. And just to remind everyone, if you do have questions, either the chat or the Q&A, preferably the Q&A section to ask questions. I've actually got about half a dozen of them myself, which I'll hold on till later. And one of them isn't whether Patatrack was named after you, but I'll leave that for later.
Sadly, no.
Thanks. We'll move on to Alec for the next section.
Yeah, hi, I'm Alec, and I'll be talking about some of the work we've been doing using cloud infrastructure for bringing deep learning into the gravitational wave physics domain. And so just a little background on the problem. When really large objects very far away start moving very quickly, they create these ripples in space-time that we call gravitational waves. The problem is because we don't happen to live near any of these objects, like black holes, luckily, by the time those waves get to us, their amplitude is so small that they're really, really hard to detect. And so LIGO is this collaboration that is represented by these two observatories in Oregon and in Louisiana that uses lasers to, at very, very high sensitivity, be able to detect these little perturbations. And so the data that we measure at LIGO are these time series of this quantity called strain, which basically measures the displacement of objects within that gravitational wave. So I'm going to hide this little panel at the bottom. Sorry. And so it's inferred from these photons that we detect as these lasers stop destructively interfering because they're being caught in this gravitational wave. But as you can imagine, it's very, very sensitive. And so environmental noise caused by, let's say, seismic activity or by magnetic fields caused by telephone wires can disrupt that perfect destructive interference of the lasers and lead to spurious photon detection, which leads to these noisy strain measurements. And so it makes it more difficult to pick up very, very low amplitude events. So LIGO leverages sort of auxiliary sensors, which can detect this environmental noise and try and predict the noise that we're going to measure at these strain channels. The problem is we need to be able to do this very, very quickly. So during LIGO's next data collection run, which is going to be called 04, one thing we're really excited about is the promise for what's called multi-messenger astrophysics, where the same event is being, ejecting multiple different astrophysical messengers, and we'd like to be able to, kind of cross-reference them to learn more about physics. So we're detecting gravitational waves, but you could also imagine there's electromagnetic waves that are emanating from these events. There are neutrinos, and so we'd like to be able to compare all these different phenomena to be able to learn more about what's happening. And so LIGO and its accompanying detectors, Virgo and Kagra, are going to play a really, really critical role to being able to detect these events very quickly and notify other observatories to let them know, hey, there's a really cool event that's about to be happening, in this corner of the sky, and make sure to collect that data. And so the faster we can do this, the more likely we're able to get data, those alerts to these observatories more quickly and collect more data as a result. And so in order to be able to do this in real time, some of my colleagues have started to look at using deep learning networks in order to perform some of these tasks of interest. So on the top left is this sort of convolutional autoencoder network we're calling DeepClean, which is used to perform that noise removal from these auxiliary sensors. And then also a convolutional neural networks for doing the kind of binary classification for detecting a specific type of event called a binary black hole merger. And so deep learning represents the potential for doing really, really robust modeling in a way that maybe more traditional models couldn't, and also doing it in real time, so without having to kind of sit around and wait to collect a bunch of data to do some sort of like offline analysis. And so the other really exciting thing was we're hoping to be able to use deep learning to do kind of more generic anomaly detection and sort of pour through vast amount of data that we've already seen, and hopefully to be able to detect new events and be able to learn new physics from that. But as Kevin and Patrick have talked about so far, achieving really good, efficient performance with deep neural networks is a really non-trivial task. So kind of taking a cue from them, we've begun to adopt this inference as a service paradigm, which allows us to be able to do really, really scalable inference very easily. And so it works both in this sort of online deployment scenario, which kind of what we talked about so far, where you want answers very, very quickly. But also, of course, in this offline scenario where we're pouring through massive amounts of data. And the point is that both of these really benefit from the cloud. Even if the model itself isn't being deployed in the cloud, we need to do really, really large scale trainings and importantly, really, really large scale validations, particularly if you're going to be automating your training pipelines. You need to be doing really, really large scale validations to make sure that your models are performing at the level that you expect them to. And so being able to elastically scale to these large amount of resources in the cloud is really, really critical for both of these applications. One thing that makes inference as a service kind of more difficult in the LIGO setting is that we have these, theoretically infinitely long time series, but our models typically act in kind of a fixed length snapshot. And so there's all this overlapping data, which creates this sort of IO bottleneck because you're just repeating a bunch of data that you don't have to send to the server. So one novel thing that we've been able to introduce in our pipeline is this sort of caching system on the inference service that's able to kind of maintain the state that we only need to stream new data, and we can therefore lower our bandwidth and be able to do higher frequency inference without introducing any extra costs or sort of IO load. And there's a similar problem when you have models like DeepClean that output time series, because a lot of these predicted time steps are going to be overlapping. And so it's, well, what do you do with these? So we've adopted this kind of naive, what we may call fully online solution, where we're just taking the most recent samples available, but there are potential benefits that we're investigating and that I'll talk about in a second from aggregating over them. So to show you kind of what's motivating this, so this is us using Inference as a service to be able to use DeepClean to remove noise from data in real time on a replay service that's happening on the LIGO data grid. And it's able to do it at millisecond level latencies. But as you can see over here, we actually, this caching step that we introduce in order to reduce our bandwidth actually ends up bottlenecking us when we do really, really high frequency inference, because it introduces this serial step that bottlenecks us. As well, that online prediction strategy that I talked about can also degrade the quality of the cleaning that happens. And these are really, really big issues if we want to deploy this in production. And so addressing these is going to require some really novel ideas, trying to figure out better ways to train the network in order to get rid of this sort of degradation in inference quality by doing this lower latency fully online prediction strategy. And so again, this is going to require tons of training and really, really large scale validations and testing in order to be able to figure out how we're going to solve this. And the quicker we can iterate on ideas and pour through data in order to validate whether this novel idea that we've tried is good, the faster we're going to arrive at a better solution. And so the resources we need to be able to do this are really only available in the cloud. And then we also performed a couple offline analysis in the cloud, try to process large amounts of data from previous data collection runs in LIGO called 02 and 03. And so you can see, so this was just using DeepClean to clean a bunch of data. And moving from this more traditional pipeline on the far right, which we are running on kind of the existing resources available within LIGO, to a cloud-based inference as a service model, even without any GPUs, we're able to achieve a full order of magnitude increase just from the adoption of this model on cloud resources. And then as we begin to add GPUs, we get another factor of 5 increase, and then sort of linear increases from there as we scale up the amount of GPU usage. On another pipeline that does both DeepClean and BBHnet, so it uses DeepClean to remove the noise, and then BBHnet to predict the likelihood of an event condition on that cleaner strain data. What we noticed is that as we add more and more GPUs, our processing time per second of data that we need to process decreases pretty linearly as we add more GPUs. And so that ends up balancing out the increase in cost per unit time that we get from using more resources, right? And so as a result, our cost stays pretty much constant as a function of the number of GPUs we're using. And that's really great news for us, because that pushes the optimal operating point out to infinity, right? If your cost doesn't change, you may as well use as many resources as you possibly can and reduce your processing time as much as possible, because it's not going to increase your cost at all. So the cloud, in this kind of huge elastic scale that we can achieve with it, and the economies of scale we get from the inference as a service model, represents a really, really powerful and cost-effective model for us going forward. Phil has talked about HepCloud, and so we've run tests using HepCloud in this environment and been able to scale up even larger than the tests that we saw so far. So we're really excited about this as an option going forward for running really, really large scale offline analyses. So in the short term, we have a kind of high priority steps for us. So we've built a lot of tools to be able to do this. We've invested in a lot of infrastructure, because it doesn't do me any good if I've built one pipeline that goes really fast. If for the next thing I want to do, I have to completely rebuild everything. So we built what we think are really, really useful tools for deploying these kind of pipelines at scale. And we're working on sort of generalizing them and open sourcing them. And then also, as I talked about, trying to research solutions to these problems we're experiencing with DeepClean in order to be able to get it into production and run it in real time. And so that's going to mean training and validating it on large amounts of data. And then we're also really excited about using BBHnet and possibly other anomaly detection algorithms in order to pour through the 02 and 03 data sets and be able to hopefully detect new events that we haven't been able to detect previously, or maybe even new types of events altogether. After that, longer term, we're interested in really putting this deep clean pipeline into production and offering other users of LIGO cleaned stray data from which they can do event detection at hopefully higher levels of sensitivity. And so this is going to mean automating training and validation pipelines in the cloud and pushing validated models to cloud-based model repositories that online deployments of Triton can read from at the detector sites themselves to the lowest latency possible inference. And so getting this into production and really trying to increase the ability of all the scientists at LIGO to use cleaner, higher sensitivity data, we think is a really exciting avenue for us going forward. And yeah, thank you.
That's great, thank you. I keep getting questions, so I've got questions myself. I'll remind everyone that I'm interested in other. Got quite a few participants here. I'm interested in whether other people have questions. I don't want to be dominating question time myself, but anyway, thank you for that, Alec. Ding Jun, I think you've got the next section on neutrinos.
Yes. Okay, so yeah, I'm going to talk about the neutrinos. And I hope you can see my slides.
Yeah, that's great.
All right. Okay. So yeah, my name is Tingjun Yang. I will talk about the GPU accelerated machine learning inference for offline reconstruction and analysis workflows in neutrino experiments. So here is just a brief introduction that the machine learning applications have become very popular in the neutrino experiments as well. And we are facing a similar challenge as for the detector, collider experiments, which is about the inference of the machine learning algorithms. And this can happen on billions of events, many times a year. And we all know that it is very slow to run the machine learning algorithms, the inference on the CPUs. So this is a big challenge for the neutrino experiments as well. So the solution is to use the GPU as a service, and we are exploring this Sonic framework, which is to run the C++ code on CPUs, and also to send the request to run the deep learning algorithms inference in the remote server by using the GPUs. So this was pioneered by the original work done by the LHC experimentalists with Microsoft Research, and was the first developed for the CMS experiment. And now we are expanding this to the other experiments like Dune, Atlas, and astrophysics. So Dune stands for Deep Underground Neutrino Experiment. It's the largest neutrino experiment so far, with more than 1,000 collaborators. And so the plan is to produce a high intensity beam of neutrinos at the Fermilab and shoot them to the detectors at South Dakota. So then those neutrinos will travel 1,300 kilometers and may turn to different types of neutrinos. So by studying the neutrinos in those large detectors, we can learn many interesting things about nature. And to prototype the detector technology, we built 2 prototypes at CERN in Europe. And so we call them the ProtoDune. And here we show the picture of the 2 ProtoDune detectors. And this picture here shows the single phase detector, and which I'm going to be focusing my talk on. So ProtoDune single phase is the largest liquid argon TPC ever built. And here is a picture of the inside of the detector. And here I give the dimensions. And so when in operation, the whole detector will be filled with liquid argon. And this large and high resolution detector will give us a lot of details about the particle interactions. And here I have a event display of a data event in protodyne single phase, where you can see the incoming pion particle interacting with the argon and produce secondary particles that can be further measured. So we developed a reconstruction chain to reconstruct those kind of events. And the reconstruction chain includes many different algorithms. And one of the algorithms is a machine learning based tool called EM-Track-Michel ID. So this EM-Track-Michel ID is a convolutional neural network. And the idea, the purpose of this network is to flag the activities in the detector as either track-like or shower-like. And there are many different types of particles we can see in the detector. Some of them are long track particles, and some of them are shower-like particles. And the network is able to give a score that tag different kind of interactions. So this network has roughly 12 million parameters. So it's a rather complicated network. And each event will have 55,000 patches. Those are the inputs to the network. So this table summarizes the inference time for both the non-machine learning module and this particular machine learning module. And you can see that this machine learning module takes 2/3 of the processing time per event. So that's 220 seconds. So clearly this will become a problem when we run the reconstruction on millions or even billions of events. So we need to speed this up. So we use GPU as a service to speed up the machine learning inference. So as Kevin already described, we have the local computing farm at the Fermilab, and we can process, run the CPU-based algorithms locally, and we can send a request through the gRPC protocol to Google Cloud and for the machine learning inference using the GPUs, and the result will be sent back to Fermilab. So here is the result of the inference time using Sonic. So as a reminder, it takes 220 seconds to run the machine learning algorithm on CPU. And with Sonic, this time, the processing time is reduced to 12 seconds. So it's a factor of 18 reduction in processing time for this algorithm, which is great. And if you look at the breakdown of this 12 seconds, you can see that there's still, the majority of time is spent on CPU preparation and also network latency. The real processing time is 2.7 seconds on GPU. So there is still room for improvements. So we summarized the test and published the result in this paper. And this was based on the work done with the simulation. So our next step, the plan for neutrino year 2, is to apply this to the real data and do the large scale production. So the plan is to reconstruct all protodyne beam events, taking advantage of the machine learning inference acceleration using Google Cloud. So in order to achieve that goal, we have been doing development and improvements work. For example, we resolved the issue with the GPU memory usage by upgrading the TensorFlow version to version 2 in our reconstruction framework. And we also added the new Sonic implementation in our framework, and also optimized the reconstruction workflow to run the machine learning algorithms in a more efficient way. So our recent production test was successful. So we are able to run the reconstruction on 50,000 events using the Google Cloud. And we extrapolated this test to the full scale production, and expected that in order to process all the 7 million Protodume beam events, we would spend 56,000 Google Cloud credits. So in summary, the test of the Protodume offline production using a GPU as a service on the Google Cloud was successful, and we plan to run the reconstruction on all Protodume beam events in the next month. And this will benefit largely the Protodume data analysis and the publication of physics results. And we are really grateful for the Google Cloud for supporting the fundamental research at the Protodume. We also have future plans. We will continue to optimize the GPU implementation with TensorRT and with tools such as quantization. We will try other hardware such as FPGAs, IPUs, and we will also explore deployment at scale at Fermilab, NERSC, HPCs, and other locations. Thank you.
Thanks very much for that, Ting. You answered actually one of my questions I had in the background, so that was good. But I'll probably still ask a variation of it. Now for the final presentation in this series, Dylan has been hyped up. There's 2 or 3 already who have said hang out for Dylan's presentation. So I'll let you take it away. Thanks, Dylan.
Yeah, hopefully I don't disappoint. Can you see the slides?
Yeah, it's looking good. Thank you.
Okay, great. So I'm going to close off this sort of session for us to talk about most of our work with FPGAs. So you've basically heard in a lot of the rest of the talks about a lot of exciting work that we're doing with GPUs, and that's for good reason. I think these are really promising accelerator hardware for all sorts of different problems and applications. But you can't solve every problem with a GPU. There are just some that have constraints that make GPUs difficult to use, and FPGAs are really, I think, an ideal solution for a lot of sort of specialized cases at, say, low latencies that don't work with GPUs or very high throughputs. And so this is a really interesting avenue of research that we've been pursuing. And a lot of our work here has been working to facilitate and understand how to best use FPGAs, because it is sort of it's a much more young field than the GPU field, I think. So you've heard about FAST a few times in the other talks here. Stands for FPGAs as a Service Toolkit. The sort of beauty of this is the interchangeability between FAST and Triton, so that you can swap between using GPUs and FPGAs. I won't go through the full suite of results that we produced with FAST, but I think the sort of general takeaway, if you look at the table on the bottom of this slide here, if you look in the red box, these are results for that calorimeter network facile that was mentioned earlier. And what you see is that the numbers in blue are those with FAST with different devices, and the box in green represents the GPU as a service number. And you see basically a factor of 4 up to about an order of magnitude improvement when you move from a GPU to an FPGA with this small calorimeter network here. If you look at a much larger network like ResNet 50, the differences between FAST and GPUs as a service are fairly minimal, and they perform similarly. And so, there are certain regimes where FPGAs are really, really great, and there are some where whether you use them or GPUs is a matter of ease and preference and other things. One of the sort of great tests that we've been able to do with these resources that I'd like to highlight is a real sort of true scalability test of how many processes can a single FPGA server really actually serve. It's great to talk about things in the hypothetical, but in order to know this, you actually have to do it. And so what we did was we started a server and we created n client processes. So that's this x-axis on the plot on the bottom right. This was all done in AWS. And then we ran a realistic high energy physics HLT workflow on these processes. And we compared sort of the standard HLT, which you'll see in this black dashed line here, which doesn't depend on how many processes you run because they're all independent. And we compared that to an HLT where we took the calorimeter reconstruction and we replaced it with fast running facile. And that's will be shown in red. And we used HepCloud to do all the management of this and make this test possible, really. And what we found, if you look at the plot here, is basically a 10% reduction in the operating time when you switched from the nominal HLT workflow to fast. And this is essentially consistent with the fraction of time that the HLT actually spends doing calorimeter reconstruction, which means that we've actually achieved basically maximal achievable performance in this setup for this particular design. If you look at the plot here as well, one other thing you'll notice is that similar to a lot of other plots like this, you basically see no change in the latency for low numbers of processes, and then at some point the server becomes overwhelmed. And this point happens with fast running the fast server at around 1,500 clients, which means a single FPGA can service 1,500 HLT instances. And this outperforms the GPU numbers, which again is what we expect given the performance numbers that we see in other tests. And actually the sort of kicker here is that this performance is limited not by the performance of the FPGA server, it's limited actually by the bandwidth, the network. So the AWS ingress is 25 gigabits per second. And so we're capped there. If we run this locally on an Alveo U250, we sort of project that you'd get to somewhere around 3,300 clients. So really large numbers. So this is really great, but Facile is a very small, dense network. It's 1,000 parameters or so. So there's, this is one type of algorithm. There's a lot of interest in much more complex architectures that I think are really sort of paving the way in how people move science forward. Two that I'll highlight here that we've developed in the past year that are really enabling some more interesting tests are recurrent neural networks and large convolutional networks. And this really greatly expands how we can use or even think to use FPGAs as accelerators. So recursive neural or recurrent neural networks are sort of a semi-natural solution to a lot of particle physics problems where you have some collection of particles like you see in these gray cones here, things we'd call jets, or you have a collection of hits or you have a collection of things basically. And the algorithm, the sort of way recurrent algorithms work is that you pass these inputs one by one to that recurrent block, and it sees them and it makes a decision, in this case, about the sort of source of this collection of particles being a light quark or a gluon in the case of these two jets on the left here, or a B hadron in the case of the top right one here. So this is a task called B tagging. We have some support for, we've worked hard to get some support for recurrent networks already in HLS for ML. And we're doing a lot of work currently to sort of fully flesh that out and make it so that we can really fully support, arbitrary LSTM GRU structures in HLS for ML. And there's a lot of cool design choices that you get that recurrent networks open up that don't exist with other architectures. So, if you have a network, say, that's processing this jet here with these three particles, or processing this whole event, say, with these three jets, you could imagine having one recurrent block that has to accept each input sequentially. So I feed in the first particle or the 0th particle from a jet, and then the first, and then the second, and then I move to the next jet and I feed in 0, 1, 2. And in this case, I have to wait basically a latency of 9 recurrent blocks, but I only have to make one recurrent block. In a sort of in another way, you could have 3 separate recurrent blocks, and then you can do this processing in parallel. You shrink the latency down by a factor of 3, but your resources go up, and so you can sort of trade this off. And this is a really sort of unexplored design space that you don't get with, say, a simple dense network. Another sort of popular architecture are large CNNs, and these are really used a lot in sort of fixed geometry problems. So this is sort of a neutrino detector here, where a scattering event happens and you have particles that come out and they deposit hits. And you have this image that you can basically look at and try to decide what the sort of fundamental interaction that happened to create this spray of particles. Big CNNs are difficult to synthesize with limited resources just because of their size. And they also involve big loops, which means they're really not ideal for HLS. So we've done a lot of work in the last year. Multiple different implementations of sort of how to handle large CNNs were explored. They were combined in various ways to sort of get the optimal performance. One network that we're really sort of working hard to be able to synthesize out of the box is a network called Deep Callow, which takes basically calorimeter energies as inputs. So you see a picture, sort of a diagram on the bottom left here of the Atlas eCal, and basically this grid here that you see represents the actual calorimeter cells, and this is basically then turned into an image, and you're trying to reconstruct the energy of an incident electron or photon that's hit these cells. This is a much bigger network than, say, Facile, so the size is around 2 million parameters, and we're very close to being able to synthesize this out of the box. There's basically some sort of functional layers that have to be hand coded, but other than that, the bulk of the CNN architectures can now be done right out of the box. One other thing that I'd like to mention is a tool called Aegean. And this is something that we designed sort of ourselves with collaborators to take a description of a large neural network and create a whole set of kernels that each represent the layers or some subset of the layers in that network. And then to be able to partition this network basically dynamically across multiple devices, which could be FPGAs or CPUs. And the sort of beauty of this Aegean framework is that it handles these connections and the bridges all seamlessly. So you don't have to do any sort of hand tuning of this yourself. It's all handled with basically a description of what your setup looks like. And then you just basically push a button and it gives you something that you can run across multiple devices, which is really doesn't exist without this. And this is really useful for optimizing, for prototyping, to be able to swap things in and out. And it's crucial for things that, say, don't fit on a single FPGA. So you'd have to run them split across multiple devices. It's also really useful for single batch inference, where you really want to just pump as much through as possible. And so to demonstrate this, we used Aegean to implement ResNet 50 across 11 different FPGAs. We ran this basically at super high throughput and low latency. And this outperforms other ResNet 50 implementations that exist from, say, Brainwave or on a GPU, V100. One other thing I'd like to mention is a tutorial series that we've done. So we basically use these tutorials to help introduce users to the tool of HLS for ML, as well as like how to accelerate things. These were first hosted on AWS, and now they're run on Google Cloud with credits from this project. More than 500 people have participated in these tutorials that we've run, which is really great. And there's offline resources that we provide and that actually enthusiastic users now provide that basically enable many, many more people to use this tool. And the idea is that it's really useful both for sort of complete beginners as well as people who maybe have expertise in ML but don't, have never accelerated something on an FPGA before. So I've tried to give you sort of a picture of the work that we've done up until this point. And I think the thing I'd like to sort of hammer home here is that a lot of the work we've done up until now, has basically opened up a lot of the tests that we wanted to do, but it's sort of necessary work that we needed to do. So this significant amount of work that went into enabling large CNNs really opens up a set of a real suite of things. So an at-scale test of running Deep Callow, sort of at scale for the full calorimeter, is a really important test of using large CNNs and using them as a service that we haven't been able to do yet without that capability. The fast server is capable of handling these convolutional networks, and HLS for ML is almost there in terms of synthesis out of the box for Deep Callow. Another thing is LIGO detection and cleaning networks are both CNN based, the two that you heard. And these can be synthesized already, and we have good results for BPHNet. We've achieved significantly reduced latencies with respect to GPUs. And the FPGA implementation for this is a really promising option for things like low power or high throughput use cases that you might find on like a satellite or somewhere where you really don't have the ability to put a GPU there. And this is indeed something that next generation experiments are looking into. And finally, these HLT tests are also a really strong use case for FPGAs. So our previous tests only really considered single algorithms for acceleration. We only took facile and replaced it, or we only took calorimeter reconstruction and replaced it with facile. And so one thing we want to do is do a real full test of a I don't know the term, multi-heterogeneous HLT, basically, with both FPGAs and GPUs. So you could envision a setup like is diagrammed on the bottom of the slide here, where you have CPU nodes and you have facile running on FPGAs and the tracking running on GPUs. And this is the first possible test with mixed hardware. And finally, Aegean is also a really innovative possibility for these really low latency, high throughput use cases that we have, like the level 1 trigger. So just in conclusion, I think FPGAs are necessarily going to be an important accelerator technology going forward because of their flexibility and the fact that they meet some of these really difficult to handle constraints that can pop up. And I think our work has already demonstrated a lot of different possibilities for this. And we've enabled some initial tests through FASTs. But now that we have some significant infrastructure and support work that's now complete, we can look to do multiple sort of new workflow tests with these developments very soon. Thanks.
Excellent. Thank you very much, Dylan. We are a tiny bit over time, but I've actually got about 8 questions that I could ask, but I'll actually just ask one, and we might leave the rest for a bit later. I'll point this at Dylan, but if Phil or any of the others want to chime in, I'd be interested to know as well. A lot of these methodologies are obviously designed for high energy physics, but do you see that the whole concept of using FPGA, well, not only FPGAs, acceleration as a service is something that is likely to catch on in other areas of science rather than just high energy physics?
Yeah, I think that's definitely true. I mean, I think we've already shown that as a service is a really compelling option for real-time processing with LIGO, which is a really different, I mean, it's a completely different sort of data flow structure that you get in high energy physics. And I think in general, as a service, the beauty of it is the sort of flexibility and scalability. And so you don't necessarily need to end up in a regime that looks exactly like the LHC in order to make use of those sort of features of as a service, I think.
Yeah, and it seems to me that a few of the cloud providers are trying to develop similar services by having accelerated machine learning and as a service. I haven't actually looked into them closely myself, but do you see that that commercial cloud providers might also follow that path? And conversely, is some of the work that commercial providers are doing on their own generic machine learning platforms potentially applicable to the work that you're doing?
Yeah, I think there's definitely a symbiotic sort of relationship there. I mean, we make heavy use of Triton, which is a tool that is developed completely by NVIDIA. I think in general, there's always going to be things, I think maybe this is a physicist point of view, but I think there's always going to be things that we will have to design ourselves, for certain specialized use cases and things like that. And I think the beauty of the current setup that we're in, I think, is that we have the ability to use industry where it really is well suited for us, and take those parts and write our own things where they need to be written.
Yeah. Okay. Thank you. Well, Phil, if you want to have any last comments, otherwise we might leave it there and just have a very quick break.
So I just wanted to add one quick thing, which is that right, when we started the project, right, I mean, there were some like industry tools and ideas, and we built on top of that. But I think the big thing that we learned from this project was how we actually integrate this into our system. Right, it's easy to say, oh, Google Cloud we have this inference as a service tool, but then the question is like, how do you actually put this in your existing software stack and actually not, overuse, right? Like balance out the throughputs between the different algorithms. How do you integrate this so that you're actually using it efficiently? And that's really what we learned in this project. So I think that's really where I think the information that we get from this can be applied to a lot of people, kind of generically, even if they're using, kind of the tools that exist in the cloud.
Very good. How did you want to comment at all or otherwise? I think you're still on mute.
Yeah, no, I think that's still did a really good job of covering it. Yeah, I've always seen this as a very agnostic platform. And I think that's what makes it so great is any pipeline can be developed without having to know what's happening on the server. And so I'm really excited about. I mean, there's no reason in the future that like the algorithms that Dylan's working on, the algorithms I'm working on, wouldn't live on the same inference service, even though our pipelines are working in completely different places on completely different problems. I think that's really cool.
Okay. All right, thanks. Well, I think we're a little over time. If there are any extra questions, we do have a panel session at the end where we could perhaps squeeze some of those in. But I don't want to take too much time away from the neuroscientists who are up next. So how about if we just pause for about 1 minute and then I'll introduce Dr. Salvador Dura-Bernal and his team and we'll get started. So just take about a 1 minute break. Thanks.